Morning, guys. So yesterday we had a look at pulley systems. We saw how we had to start studying the entire system to find the overall acceleration. Remember, what's misleading about these pulley questions is we just take a quick snapshot of what the pulley system looks like at that moment. If I run the clock, it will probably start accelerating either in one direction or the other direction. We saw how that the string can actually transmit the force. It can actually turn the corner around the pulley, but based on Newton's third law, we knew that the string's force is always equal and opposite. So let me give you a quick practice question with pulleys, and then afterwards we're going to deal a little bit more with the gravitational concept. So just as a quick warm-up here, let's imagine we have actually two tabletop pulleys, so one on either side. We're going to have three masses in this case here. I'm going to keep the numbers fairly simple. Let's say mass number 1 is a 10 kilogram mass. It's hung over a pulley. It's connected to a second mass here. This second mass here is just a 5 kilogram mass. And then there's another string hanging on the other side here. We happen to have a 30 kilogram mass. I'm going to give you that the coefficient of friction here, let's say the mu is actually 0.20. And we're interested here, always the same style of question here. Can you calculate the acceleration of the system? So if you think about all three of these, they'll either all fall clockwise or they'll all go counterclockwise. At what acceleration rate do they do it at? And then B, I want you to determine or find the tensions. In this case here, because I have two strings, I will have one string that has a T1. That T1 is actually pulling on both sides there. And I will also have a T2. When we said equal and opposite, we just said along one string itself. But because these two strings here are totally unrelated to each other here, the amount of tautness or tightness along the one side doesn't actually have to be the same as on the other side there. So I've already sort of started sketching out for you here. We want to do a free body diagram. I would pause this video and you can try it out for yourself. What we're going to have here is we're going to have an FG1. Our FG1 is going to be m times g, so 10 times 9.8. That gives me here 98. Going upwards, we had just said, it's going to be a T1 going upwards. On this mass here, we have a T1, we have a T2. On the other side here, this second mass actually also has a gravity force. So this one here, let's call it FG2. FG2 is going to be 5 times 9.8, so that should give me 49. We know that this object can stay on the table because it's actually supported by the table surface itself. You will only have a normal force if you're actually on a surface. In this case here, I know my normal force, where I don't have a formula for it, but normal force just pushes what it needs to make sure that gravity doesn't win with 49, the normal force actually has to be 49. Why do we care about normal forces? Because our friction force actually depends on it. If I try to do our formula, Ff is equal to mu Fn, my mu was given to me as 0.20. I can calculate over and I can see if I can get 49 for my normal force. 0.2 times it by 49 gives me 9.8. Right? So that's the friction force here. There's a sort of a general overarching question here. So the 5 kilogram is just sitting in the middle of the table here. Well, just looking at these sides of the masses, I have a 10 on one side, I have a 30 on this side. If you were to guess which way the system would go, which way would it be? Well, probably I'd imagine we'd fall towards the heavier side. And in that case there, if our guess is we would actually move to the right-hand side, because motion is to the right, I would actually say friction is actually to the left. And friction is actually 9.8 going in the leftward direction. And that was just purely off a guess, because I'm looking at the numbers here by inspection. I'm sort of seeing this one here should be able to fall to the right. We'll see what we get from there. On the last mass here, like a free hanging pulley here, we have a FG3. FG3 this time is a 30 times it by 9.8. This is the heaviest mass. 30 times 9.8 gives me here 294 newtons. And then overall we have, again, a T2 going up this way. All right? So first part is to do Newton's second law, but we're going to do it to the entire system all at once. So I'm going to think of the system here. I know we are sort of interconnected by strings here. But you can imagine here, I have a 10 kilogram. I have an FG1 that's trying to pull it 98 to the left. I have my first string, which is a T1 on this side. It's also a T1 on the other side, so these T1s cancel out. Then I get to my second mass here. We have a 5 kilogram. We had said there's an extra friction force of 9.8. So there's a friction force that goes that way, friction force of 9.8. And then continuing onwards from there, there's also a T2. This string here pulls us 5 kilogram to the right. There's a T2 that actually is cancelled out by the T2 supporting the 30 kilogram mass here. So our mass of 30 kilogram here, the tensions basically cancel out when we look at the entire system, and all we're left with is an FG3, which is trying to pull the whole thing to the right. So because I have the free body diagram, I don't need to worry about positives and negatives. I can see FG3 is trying to pull it to the right. These tensions are equal and opposite. They're going to cancel along T2. The T1s are going to cancel. So all I have here is we have FG3 that's pulling 294. That's on its own team. On the other side here, FG1 was trying to keep it. On this side here, the friction is also trying to help it. It's basically a tug of war between FG3 minus these two guys here. So when I try to do my Fnet, when I try to find out how much overall unbalanced force it is, I go bigger minus smaller. I take FG3. I'm going to minus off how FG1 is fighting against me, and I'm also going to minus off FF. I'm even going to show this here as FG1 plus FF, because I wanted to show you that in this case here, FG3 was a force that was causing me to go clockwise. The FG1 and the FF were trying to keep the system either stationary or even going anti-clockwise or counterclockwise. Those are two different directions, so therefore it's one minus the other one. You will also notice when I did this here, I didn't need to have a force of gravity term on the middle, because we saw that the force of gravity actually had cancelled out by the normal force there. So it's only the resulting friction force that's usually the case in a tabletop pulley. All that is equal to mass times acceleration. This time my mass has to be the total combined mass of the 10, the 5, and the 30 to get to our acceleration. So let's just try it out here. My biggest number is 294. That's trying to drag the whole system to the right. We minus off just the 98 on the 10 kilogram mass. We minus off an extra 9.8 for the friction. You can either add these numbers first and say, oh, in total it's about 110 kind of against me, or you can minus the first minus the second one. And this gives me my total mass. My total mass is going to be 10 plus 5 kilograms plus 30 kilograms all over acceleration. Because these are all hooked up by strings, they all have to accelerate in the same direction. It's not like one can go one way and the other goes the other way. They all have to go at the same acceleration, or else the strings are going to snap. So let's go 294, let's minus off the 98, minus off an extra 9.8. In total, we still have a net win of 186 going to the right. It's pulling all three masses, so that's going to be 45 kilograms with an acceleration. The total system's acceleration, 186 divided by 45, gives me here 4.1 meter per second squared. With the acceleration, you could do a lot of kinematics again, like V is equal to V naught plus AT and all that. In this question, part B was just interested in asking for the tensions. While I knew tensions were equal and opposite per string, because we have two separate strings here, we need to calculate the tensions individually. And what we saw here, our technique was, once I know the whole system's acceleration, I can just zoom in at different parts again. I can just zoom in on mass number 1. Let me just double check my numbers here. I have 10 kilograms. We had a T1 that was pulling upwards. Our force of gravity was just 98 newtons going downwards. Because the T1 is on this side here, I know that the acceleration of 4.1, the acceleration is actually up this way. By doing that one there, I can actually calculate what the T1 is going to be. On the other side here, I had a 30 kilogram block. We had an FG, I believe it was 294. This one here, it was actually a T2 because it was for the second string. And in this case here, on the other side, we are going to end up falling clockwise. So the acceleration is also going to be 4.1. To make sure we don't need to worry about negatives for acceleration, we just go bigger number minus smaller number. If I try to do F net equals ma just for this mass here on the left-hand side, between T1 that's trying to support it going upwards and FG1, we're going to have T1 minus 98 has to equal to my mass of 10 times 4.1. You'll notice I have all the numbers except for the T1. So just crunch your way through here. T1 minus 98 is equal to 41. The T1 is now equal to 41 plus 98, 139. You'll notice I haven't seen that number anywhere, even though indirectly it's somehow related to, well, it's the other mass that's eventually pulling the system upwards, it's supporting everything. But because the whole thing is actually accelerating, this number is not a direct match of 294. In a similar fashion on the other side here, well, when I'm on the other side, I know that the FG actually wins. If I try to go F net equals ma, we go bigger number minus smaller number. So we go 294 minus off whatever T2 is along the second string. is equal to just this mass, 30 kilograms. This mass also needs to accelerate at 4.1 because I went bigger minus smaller. I can keep this acceleration as positive. So let's just clean this up a little bit here. 294 minus T2, 30 times 4.1 gives me 123, and therefore T2, 294 minus 123 gives me here 171 newtons. Right? So I have the individual tensions on the different sides there. If you wanted to just verify for yourself, the middle block here is probably the hardest to check here. It has a T2 going in one direction. It has a T1 being pulled along the string, and it also had a friction force. We had guessed that the system here goes to the right. You can try it out for yourself. If I go T2 minus the combination of T1 and FF, that's going to be the net force. That equals to this mass times the acceleration, also 4.1. If you punch in both, it should end up equaling, or you punch in just one of them. When you solve for T2, it should give you the other number there. Right? So that's how we do with pulley sort of setups here. We study the entire system altogether, find the overall acceleration, and then we apply Newton's second law just to the individual parts by itself. What I'm going to switch over here is we're going to now have another look at gravitational concepts. This time, I know we've been using the formula mg a whole lot. We've been using g as 9.8. We'll actually get a formula today to actually calculate what's the equivalent of 9.8 on other planets. So we'll do a small section here on universal gravitation. It's nearing the end of our chapter here. So universal gravitation. Remember, we started off this chapter looking at, well, gravity, we can picture it as a force. Again, if you go on to physics, you're going to realize, again, it's that weird bending of space-time. Let's say I have the mass of the Earth here. I have the mass of the moon. The moon is a little bit tinier. Right? I can call it M1 and M2. Gravity is always an attractive force. It always pulls masses together. So we have an Fg and an Fg. Newton's third law guarantees me that these forces are equal and opposite. So gravity is the attractive force between two masses here. We don't see the Earth actually accelerate towards the moon. It's just because the Earth's mass is so humongous in comparison to what the moon's mass is. So even though they do also have a center mass point where they actually both sort of rotate around, we pretty much only see, well, the moon has a smaller mass here. We can see that one in orbit around the Earth's surface. So I'm just going to make that little note here from Newton's third law. So Newton's third law. This says here, forces exist in equal and opposite pairs. So, in our picture, the Earth pulls on the moon, and the moon pulls on the Earth. Let's say the same newtons, so the same force. So if, let's say, Fg was 1,000 newtons, right? That 1,000 newtons would explain why the moon is accelerating, why it stays in orbit around the Earth's surface, but it's also going to be 1,000 where the moon actually pulls on the Earth as well. Forces are always equal and opposite. These objects here, they orbit around their center mass point. It's just that, again, because the Earth's mass is so heavy, the center mass lies really, really close to where the actual center mass of the Earth is. What we're going to do here, because we're starting to talk about planetary size objects here, instead of just doing a simple m times g, again, we'll come back to why that g is 9.8, we're actually going to derive a new form. This is actually Newton's law of universal gravitation. So you can take any two bodies in space here, and I can predict what the gravitational attraction is between them. You have this on your formula sheet, and it says here, slightly more complicated than the one before, Fg is equal to g m1 m2 all over r squared. Right. So let me just qualify these terms here. Fg is still force of gravity, like it has been for the longest time. Force of gravity here, that's measured in newtons. This g here is actually a proportionality constant. This is actually a constant in our universe. So since our universe was created here, our universe always has this number 6.67 times 10 to the negative 11. It's going to have a really funny set of units. Newtons meters squared per kilogram squared. It just dimensionally needs to get rid of all the units for the other ones, because I'm going to be multiplying by these m's here are the individual masses. We talked about gravity here being an attractive force between things that have substance, things that have kilograms to it. because I'm going to take two things that have kilograms here, I need to cancel out the kilograms. But because I'm ending up going to divide it by r, this r here actually stands for a separation distance. It's how far apart things are. And you'll notice that this is actually in the denominator. So therefore, the farther away things are, let's say the separation is a little bit bigger, the force of gravity is actually weaker. So these two are actually opposite each other. This one here is a distance. We are taking the square of that one there. So this is going to be in meters, and that's something else that the unit has to cancel out. So no matter what question you do, the gravitational constant will always stay the same. That 6.67 will always stay the same. I mentioned to you, even as you encounter other people, there's always a gravitational attraction between, well, you have mass, the other person has mass. There is a gravitational pull that is pulling you together. But how come I don't feel it? Again, it's because this gravitational constant here is so tiny. It's only until we get to really like planetary sized masses that we actually end up seeing this impact. Sometimes in this formula, they'll say gmm over d squared, like d for distance. Sometimes they say r here. It doesn't really matter. If they say r, they're sort of talking about, well, usually we're talking about in orbit here. Yeah, I know that's sort of how far away that these masses are, but this is still the radius of my orbit, right? The moon is always revolving around the Earth planet here. We can call that separation distance the radius as well. What you're going to find is this formula here is actually not all that hard. But because there's a lot of powers to deal with, you're going to have a lot of trouble actually just practice typing it into your calculator. Sometimes I get people showing me all the right numbers in their problem, but somehow they're number crunching, they didn't put brackets, or they missed an exponent, they missed a square, and they somehow don't end up with the right answer. So let's just practice through here. Do pull out your calculator so you can actually try this out for yourself. I'm going to give you a few constants here. These will be on our new formula sheet. 1.74 times 10 to the 6 kilograms, the mass of the Earth. It's actually a good question here. Well, how do they actually know these numbers? Right? But for another time. Let's just deal with this one here. The distance between the moon and the Earth, I'll just say ME like that. The distance or the radius of the orbit is 3.84 times 10 to the 8 meters. So if you think of this here, this is the radius of the moon's orbit. That's why you sometimes even call that r. I can just draw this picture here. I have two masses. One of them is the Earth. That's m1. One of them is the moon. That's m2. They're separated by a distance of that 3.84 number. That one there, as I mentioned, is the radius of the orbit revolving around. What I want you to calculate here is calculate. Using this law of universal gravitation, you'll know to use this law when we're talking about planetary sized objects here. I want you to calculate the force of gravity. Right? If Newton gave you an expression, a way of actually calculating the attractive force between two objects, let's just plug and play here. So you're going to go to your formula sheet here. It says here Fg is equal to gmm over r squared. I'm going to plug through the numbers. It's already isolated for the variable that I want. The g is always a constant, so it doesn't matter, oh, I'm talking about the Earth and the moon, or the moon and the sun, or you and the person next to you. It doesn't matter. This constant is always 6.67 times 10 to the negative 11. The two masses, I'm going to end up multiplying them anyways. It really doesn't matter which mass you say is which. Usually I put the heavier mass first. So the planet that we're on is Earth, so 5.98 times 10 to the 24. The moon itself is 1.74 times 10 to the 6. You see a lot of sort of scientific notation come in here. Really make use of that EXP notation, because that way we don't need to worry about brackets. And then we're going to find sort of our separation distance. Our separation distance is 3.84 times 10 to the 8. But it's not just the separation distance, it's the separation distance squared. So how I would type that part in the calculator, instead of worrying about brackets, or where do I put brackets or whatever, I might just type in divide this 3.84 times 10 to the 8, and I just press divide it once, equals, divide it again, equals. I just press it twice to do the square there. So try typing this in for yourself here. Make sure you're able to get the calculator to get this number for you. 6.67 e negative 11 times 5.98 e24 times 1.74 e6 divided by 3.84 e8, and I'm just going to press that equal symbol twice, divide that, basically is r squared. You should be getting 4706, so that's just right here, 4,700 newtons. Right? Make sure you practice on your calculator. Again, the formula itself is not all that hard to work with, but it's just a matter of dealing with all these brackets and exponent notation. Sometimes you might get a little bit challenged. And of course, because this is a formula, if they give me sort of other sets of variables, I can find what the unknown is. Right? We'll get a little more practice with this a little bit later on. there's another way they could ask this question here is just sort of comparing it by ratio. In this case here, we're sort of talking about one planetary size object, let's say M1. The other object here is M2. We're separated off by a distance d. Maybe they're not in orbit around each other. I don't want to say r there. Let's say in this case here, our Newton's law of universal gravitation says Fg is equal to gm1 m2 over r squared. Now, had they given you the masses, they give me the distance, I can definitely crunch in the numbers and I can actually calculate what the force of gravity is. But sometimes what they're interested in is just a relative. They're going to say, okay, so I have m1 and m2. What if I compare this picture here? I'm going to keep m1 the same. I'm going to keep the distance the same. But what if I take the mass 2? And what if I had a sort of a moon that's 3 times mass 2? Right? So what's happened here is I've actually multiplied that mass by 3. What I'm going to do is I'm going to say relative to the initial Fg. So I'm not actually asking you to calculate the numbers. I'm not saying like what is the actual number of newtons. I just want to say compared to the beginning, compared to the original mass 2 here, now that this is 3 times as big, what's happened to Fg? And all you're going to have to do here, so we have a new Fg here. Our new Fg is equal to gm m over r squared. And if you notice, the only difference I did, I kept mass 1 the same, I kept the distance the same here. The only difference here is this m here. This m is actually 3 times what the mass 2 used to be. Whenever I have constants like that, I just got to pull it up to the front. The 3 comes out front here, and we're actually going to get 3 times the initial gm1 m2 over r squared. So, more so in a sort of multiple choice kind of style here, they're just interested in asking you, relative to the start, when I triple the mass, I would expect that the force of gravity is actually 3 times as stronger. So force of gravity is actually 3 times larger. Right? So without actually having you to punch in the numbers and worry about brackets and exponents, things like that, I can just say relative to the beginning, 3 times bigger. Now, what if we did one more practice here? I take this new system here, so I have an m1, I have a 3 m2, and what if all I do here is I double the distance? So my original distance used to be like this. What if I measure another distance like this? And what if my new 3m2 is actually out here? How does my new gravity, my Fg, compare to the initial gmm over r squared? And all you're going to need to do is you just need to track through your changes here. Well, compared to the really beginning, the gmm, I had gm, we had 3 times m2. I already was 3 times the gravity from before. This time, I have my distance being doubled. Careful, that's actually going to just change the r itself. Once you actually double the r, you still need to square it. So this is actually going to be 2d all squared. If you do the math there, this would end up being, again, you can pull out the 3 in front. The 2d all squared on the bottom actually ends up as a 4d squared. It's like 2 squared d squared. And therefore, I'm going to have 3 gm with m2. And if you just sort of match it up to the beginning here, the beginning was this expression. It was gmm over r squared. The constants that I ended up pulling out was actually this 3/4. So this one here is actually 3/4 that of the original Fg. So this is just asking you to do it by ratio, to do it by comparison, not necessarily having to plug your way through all those numbers. Right? So that's one way of setting it up here. They can give you all the constants, all the numbers, you crunch it through your calculator, or just in comparison, well, if I change this to the mass or do this to the distance here, you can figure out what factor is being pulled out. Last thing I want to touch on in this lesson here is something we refer to as gravitational field strength. Just another way of looking at gravity. And how this gravitational field strength works out is, if you imagine, okay, so we are on the Earth's surface, so mass of the Earth. We've been like standing on the Earth's surface. I've been taking boxes of certain mass. You know how we've been using the formula, oh, if I have a box on the ground, I've been using the formula Fg is equal to mg. How come my formula looks so much easier than the formula that they just gave me here? Well, we can actually compare it. Well, how does this relate to the universal gravitational formula? Gm1 over m2 over r squared. It turns out if we are always assuming, so I'll write this down for you here. Let's assume objects are on Earth. So that means one of the masses is always going to be the same. It's that 5.98 number that I did from earlier. The m1 is always going to be the same. Assume objects are on Earth. And also assume that we're actually close to the surface. So therefore, under those two assumptions, we are actually always going to be sort of one radius away. If you later on have a box that's twice as big or 10 times as big or whatever, you'll notice the mass of the Earth didn't change. We're still the same radius from the Earth. That actually adds to the gravitational constant here. We can actually just hide this part here, and I can actually calculate that this part here is actually going to end up as the acceleration due to gravity. This is actually going to be called the gravitational field strength. So if you just sort of compare the formulas here, when I've been using m times g, I've been looking at what's my new mass, but I've been multiplying by 9.8. That means that this g here should actually end up as 9.8. Let's see if that's what it gives you. The gravitational field strength, that's just the name for it. Gravitational field strength is given by gm over r squared. It's sort of like I pretend the mass I'm looking at is not there. There's a test mass, so it's gone. Let's just calculate through with the constants. 6.67 times 10 to the negative 11. The mass of the Earth was that 5.98 number I gave you from earlier on your formula sheet. Divided by the radius of the Earth here, 6.37 times 10 to the 6. I think I gave you that number earlier. Maybe not. Radius, no. So I gave you the orbit here. So I would just note to you, you would just look up this number. This one here is actually the radius of the planet, given the radius. And if you just work that math through, when you work that math through here, 6.67 e negative 11 times 5.98 e 24 divided by your 6.37 e 6, and you do that division twice at the end because there's a r squared. This gives you here roughly, give or take, getting 9.83 or so, so rounded to 9.8 meter per second squared. So in fact, that g that we've been using for all this time, right? We've been doing cart problems and slope problems, and we've just been multiplying the acceleration due to gravity. That 9.8 actually hid the real universal gas constant. That's the same for every problem. But what it's hid is it's assumed we were on the Earth's surface, which we are, and we've been assuming that we're one radius away because we're close to the surface. So what that allows us to do here is, for the Earth and being one radius away, instead of always having to type in gm over r squared every time, well, that just ends up as a constant 9.8. Now you can change your mass all you want. As long as you multiply by 9.8, you've gotten the force of gravity. The force of gravity is how hard the planet, it's of a constant mass of the Earth, and we're a constant radius away. In fact, this whole concept here of gravitational field here does exactly that. Let's pretend we don't know what the mass is. What this formula still gives you is it gives you what is the acceleration. If I imagine there's a certain acceleration that goes sort of towards the center of the planet here, if I had a certain mass here, how much force would I feel by the time I told you what that mass is? This gravitational field here is going to be inverse to the separation distance. So as I get further and further out, I'd imagine the arrows, they're still trying to attract me towards the center of the planet, but the force, the size of it is actually not going to be as big as it was before. And as you go out from there, it gets weaker and weaker, so that the instant that you tell me what my m is, right, that's my test mass. If you tell me, oh, I actually have a mass of 50 kilograms here, all I would need to do is I take the mass of 50 kilograms, I multiply it by the gravitational field at that distance. We've been using 9.8 because we've been close to the Earth's surface, but the g is going to change as I get farther and farther from the Earth's surface. We do that more in Physics 12. But as I get further and further away, if you just tell me what the mass is, I just multiply the field at that point, and I've gotten the force of gravity. So the gravitational field strength here is basically, this is the force a test mass would feel at that particular separation distance. So just give me the mass, I can multiply it, and then I have the force. But without that second mass here, I don't quite have a force yet. Force needs both masses to attract to each other here, but at least I have that 9.8 number. Then you can change, the mass hanging off my pulley is 10 kilograms or 50 kilograms, or on a cart problem, lawnmower problem, whatever. You can just multiply. Yes, we have been calling it acceleration due to gravity. We're just giving it a new name this time. We're calling it gravitational field strength. Okay. So that pretty much ends off our chapter. We'll do a quick lesson just to summarize some of the major concepts, and we'll go from there. Thanks, guys.